Picture a world where every word in a language is just an arbitrary index in a giant lookup table, where the word cat has no more relationship to kitten than it does to bulldozer. That was essentially the state of natural language processing for a long time. Most systems treated words as atomic symbols, and while you could get surprisingly far with simple statistical models like n-grams trained on enormous amounts of text, you hit a wall. There's no way for the model to know that Paris and Rome are similar kinds of things, or that walking and swimming relate to walked and swam in the same grammatical way. This paper from Tomas Mikolov and colleagues at Google in 2013 set out to fix that, and in doing so, it produced one of the most influential ideas in modern machine learning: word embeddings learned at massive scale, the technique that became known as Word2Vec. The motivation is grounded in a real practical problem. For tasks like machine translation or speech recognition, the amount of high-quality training data is fundamentally limited. You can't just keep scaling up n-gram models forever because there isn't enough in-domain text. So researchers had been exploring distributed representations, where each word gets mapped to a dense vector of real numbers, maybe 50 to a few hundred dimensions, and semantically similar words end up near each other in that space. The dominant approach used neural network language models, where you train a feed-forward or recurrent neural network to predict the next word given previous words. And as a side effect, the network would learn useful word vectors in its input layer. The trouble was computational cost. These models had non-linear hidden layers and dense projection layers, which meant training was slow, vocabulary stayed small, and dimensions stayed modest. Nobody had managed to train on billions of words with vocabularies in the millions. The author's key insight is almost rebellious in its simplicity. They asked, what if the hidden layer, the very thing that makes neural networks expressive, is actually the bottleneck we should remove? Maybe a much simpler model trained on vastly more data would produce better word vectors than a fancy model trained on less. Think of it like the difference between hiring a brilliant tutor who can only meet with you once a week versus a competent tutor you can see every day. Volume of exposure can beat sophistication of the teacher. So they propose two architectures, both stripped down to almost nothing. The first is the continuous bag of words model, or CBOW. You take a window of context words around a target word, say 4 words before and 4 words after. Look up each of their vectors, average them together into a single vector, and then use that averaged vector to predict the middle word. There's no hidden layer, no non-linearity, just averaging and a final classification step. The second architecture is Skip-gram, which flips the relationship. Instead of using context to predict the center word, you use the center word to predict each of the surrounding context words. For every training word, you sample a small window of nearby words and train the model to make the center word's vector good at predicting each of them. Two design choices make this practical at scale. First, the output layer would normally require computing a softmax over the entire vocabulary, which for 1 million words is brutally expensive. They use hierarchical softmax with a Huffman tree, where frequent words get short binary codes and rare words get longer ones. Instead of evaluating 1 million output units, you traverse a binary tree with depth roughly logarithm of the vocabulary size, weighted by word frequency. Second, they implement everything in dist belief, Google's distributed training framework, running 50 to 100 model replicas in parallel with asynchronous gradient descent and AdaGrad for adaptive learning rates. The really striking finding is how they evaluate quality. They build a test set of word analogy questions. Things like, Athens is to Greece as Oslo is to what? Or big is to bigger as small is to what? They answer these questions purely with vector arithmetic. You take the vector for Greece, subtract the vector for Athens, add the vector for Oslo, and look for the nearest word vector in the space. If the geometry of the embedding has captured the right relationships, the answer pops out as Norway. The test set has about 19,000 questions split between semantic relationships like country capital pairs and syntactic ones like verb tenses or plural forms. Reaching the right answer requires the model to encode these relationships as consistent directions in vector space, which is a much stronger demand than just clustering similar words together. The results are remarkable. The Skip-gram model, trained on 783 million words with 300 dimensional vectors, hits 50% accuracy on semantic analogies and 56% on syntactic ones, dramatically outperforming previous approaches like the Colliber-Weston embeddings, Manet's vectors, and even Mikolov's own earlier recurrent network embeddings, some of which scored in the low single digits on semantics. The CBOW model is faster to train and does slightly better on syntax, while Skip-gram dominates on semantics. Scaling experiments show a critical lesson. You need to grow both vector dimensionality and training data together. Doubling one without the other gives diminishing returns. With distributed training on 6 billion words and 1,000-dimensional vectors, accuracy climbs above 65%. Their CBOW model trains on 1.6 billion words in under a day, where a recurrent network language model on a comparable corpus had taken roughly 8 weeks. Now for the perspective. The simplicity that makes Word2Vec so powerful is also its limitation. Each word gets exactly one vector, so polysemy is lost. The word bank gets one representation that smashes together riverbanks and financial institutions. There's no handling of morphology, so the model has to learn from scratch that walk and walking are related, which it does surprisingly well but imperfectly. Multi-word entities like New York are excluded from the test set entirely. Synonyms count as wrong answers in the evaluation, which means the metric understates real semantic understanding. And while the linear analogy structure is remarkable, it isn't perfect, and later work has shown it's partly an artifact of how the questions are constructed. Still, this paper opened the door to treating words as first-class geometric objects, and that idea propagates forward through Glove, ELMO, and eventually the contextual embeddings inside modern transformers. Now let's walk through some questions you might have after hearing all of this. First, why does removing the hidden layer actually help rather than hurt? The intuition is that the hidden layer was doing two jobs at once: learning word representations and learning complex predictive patterns on top of them. By stripping it away, the model is forced to push all the useful structure into the word vectors themselves. And because training is so much cheaper, you can show the model orders of magnitude more data. More data exposure with a simpler model wins because word meaning is fundamentally a statistical regularity that emerges from co-occurrence, and you don't need a deep network to extract it. Second, why do analogies work as simple vector arithmetic? This is genuinely surprising, and the paper doesn't fully explain it. The intuitive story is that during training, the model is pushed to encode each word as a sum of its various relational properties. The vector for king ends up containing a royalty direction and a male direction, while queen has the same royalty direction but a female direction. When you compute king minus man plus woman, you cancel out the male component, add the female component, and land near queen. The linearity emerges because the training objective is essentially linear in the vectors before the softmax, so the geometry organizes itself in additive ways. Third, what's the real difference between CBOW and Skip-gram in practice? CBOW averages all the context words together and uses that average to predict one target, so it's faster, but treats the context as a blurred bag. Skip-gram makes a separate prediction from each center word to each context word, so it processes more training examples per sentence and ends up with sharper representations, especially for rare words. The trade-off is that Skip-gram is slower to train, but typically yields better semantic quality, while CBOW is the better choice when you have huge corpora and need speed. So, how does this connect to large-scale recommendation systems? The core idea translates almost directly. If you replace words with items, products, videos, or songs, and replace sentences with user interaction sequences, you get item embeddings learned from user behavior. This is essentially what powers candidate retrieval at companies like YouTube, Spotify, and Pinterest. You train a Skip-gram style model on sequences of items each user engaged with, and items that get consumed in similar contexts end up with similar vectors. At serving time, you can use approximate nearest neighbor search over these embeddings to retrieve candidates in milliseconds, which is far cheaper than scoring every item with a full ranking model. The deeper lesson for production systems is the scaling principle. Simple architectures trained on enormous interaction logs often beat sophisticated models trained on smaller slices. Hierarchical softmax and negative sampling tricks introduced in the follow-up papers became standard tools for handling catalogs with hundreds of millions of items. And the analogy structure has practical use too. You can do things like items popular in this geography minus this geography plus another geography to handle cold start localization, or compute user embeddings as averages of recently engaged item vectors for lightweight, real-time personalization without retraining heavy models. Word2Vec's legacy in recommendation systems is the realization that representation learning over behavioral sequences is foundational infrastructure, not just an NLP technique.